Hello everyone. In this video we shall see how to derive a few expressions from the chapter of electrostatics that will be important for your board examinations, both Cbse and ICSE. So this derivation will be on intensity of electric field due to an electric dipole at axial, which is also known as end-on position, and also at equatorial, which is known as broadside position. So let's just start by writing down the definition of intensity of electric field. So intensity of electric field is the force experienced by a unit positive test charge kept at a certain point in the electric field. And the expression of electric field, the expression for intensity of electric field due to a point charge Q is given by E is equal to 1 by 4 pi epsilon naught Q by R square, where we are determining the intensity of electric field due to the charge Q at a distance R from it. And the direction of intensity of electric field, which is of course a vector quantity, is towards the charge E is towards the charge if the charge is negative, and E is away from a positive charge. Next comes electric dipole. So what exactly is an electric dipole? So electric dipole is a system of two equal and opposite charges separated by a certain distance. So let us consider two equal and opposite charges, minus Q and plus Q, their distance of separation being 2L. So this constitutes an electric dipole. The strength of the electric dipole is given by the quantity named electric dipole moment, which is defined as the product of P, which is electric dipole, is defined as the product of the magnitude of the charge and the distance of separation, which in this case is 2L. The quantity electric dipole moment is also a vector quantity, its direction being always from the negative to the positive charge. The direction of P, that is the electric dipole moment, is always from negative to the positive charge of the dipole. With that being said, we would like to now come to our derivations of intensity of electric field due to an electric dipole at number 1 being the axial position, which is also known as end-on position. So what exactly is this axial position? Axial position is a point which lies on the axis joining the two charges of the dipole. Suppose this is the charge minus Q of the dipole and this is the charge plus Q. Then the line joining these two charges will be their axis, and any point on this axis, let's say the point P, will constitute the axial position. So what is the distance of separation between the two charges of the dipole? It is always 2L, and the point P is on the axis is located at a distance of r from the center of the line joining the two charges of the dipole. So the distance between the plus q charge and the point P will be r minus L, and the distance of the charge minus q from the point P will be r plus L. Now let E1 be the intensity of electric field at P due to the charge minus Q. Therefore, the expression of E1 will be given as 1 by 4 pi epsilon naught Q, and the distance of the point being R plus L to the power 2. Now what will be the direction of the intensity of electric field due to the negative charge minus Q? Away from itself, that is away from minus Q, because for negative charge the direction of this will be towards the charge minus Q, and as we have discussed, the intensity of electric field due to a negative charge will be always towards itself, towards minus Q. And on the diagram I'll be showing the direction of E1 in this way. Now similarly we shall be writing down the expression for intensity of electric field at P due to the charge plus Q. Intensity of electric field at P due to the charge plus Q is E2 is equal to 1 by 4 pi epsilon naught Q by the distance between the charge plus Q and P being R minus L. So divided by R minus L whole square. And what will be the direction of E2? It will be away from the positive charge. So in the diagram I shall be marking E2 away from the positive charge. Now at the point P we have two different electric fields that are acting in opposite direction, and we know that when two vectors act in opposite direction, the magnitude of the resultant vector will simply be the difference between the two magnitudes. So the resultant intensity of electric field at P is E net. It should be always be the greater minus the lesser. Which one is greater? Obviously E2 will be greater than E1, because in the denominator of E2 there is R minus L, and in the denominator of E1 there is R plus L, and we also know that lesser the denominator, more will be the quantity. So here the denominator is less for E2, and hence E2 will be greater than E1. Now I substitute the values of E2 and E1. It will simply be 1 by 4 pi epsilon naught R minus L whole square minus 1 by 4 pi epsilon naught Q by R plus L whole square. Now what I'll do is I'll take 1 by 4 pi epsilon Q by 1 Q into 1 by 4 pi epsilon naught common, and this will be R minus L whole square minus r plus L whole square. Now all we need to do is simplify this expression. So what will be the LCM between the two quantities? R minus L whole square into r plus L whole square, and so it will be in the numerator r plus L whole square minus r minus L whole square. Now you need to just open up the bracket in the numerator. This will be r square plus L square plus 2rl minus r square minus L square plus 2rl, and in the denominator it is r minus L into r plus L, that is r square minus L square. Now both the terms are raised to the power 2, so r square minus L square will also be raised to the power 2. Now in the numerator we can cancel out r square and L square, so overall we'll get q by 4 pi epsilon naught 4rl by r square minus L square whole square. Now 4rl I can write it as 2r into 2ql divided by 4 pi epsilon naught r square minus L square. So what does this quantity 2ql represent? This quantity 2ql represent the dipole moment, as we have seen, that is 2l into q. So instead of 2ql I can straight away write p, which is your dipole moment. So the resultant electric field at the axial position is given by 2r into p by 4 pi epsilon naught r square minus L square whole square. And what will be the direction of the resultant electric field? The resultant electric field will always be in the direction of the quantity which is greater. What was greater? Which quantity was greater out of E1 and E2? The quantity E2 was greater. So the resultant electric field will also be in the direction of E2. This will be your E net. And what is the direction of the dipole moment P? The direction of dipole moment, as we have discussed, is always from the negative to the positive charge. So vectorically, resultant electric field and the dipole moment are parallel to each other. So we can write E net vector is equal to 2r by 4 pi epsilon naught r square minus L square p vector. So these two are the scalar expressions, scalar and the vector expression respectively. Now one more thing that is important with respect to these expressions is the expression for short dipole. So what exactly is this short dipole? A short dipole is a dipole whose length is very small compared to the distance of the point. The length of the dipole being L and the distance being r, so we can say that r is far greater than L. So for a short dipole in these expressions we can neglect the value of L. So as you can see in the denominator there is r square minus L square, and if r is far greater than L, then we can just neglect L square. So r square minus L square will be equal to r square. So substituting it in the expression of E net, 1 by 4 pi epsilon naught 2p r square minus L square, 2pr r square minus L square whole square. And the denominator we can just write r square minus L square as r square. So this can be further simplified as 1 by 4 pi epsilon naught 2pr by r to the power 4. There will be some cancellation. R by r to the power 4 will give you r cube. So E net becomes 1 by 4 pi epsilon naught 2p by r cube. This is the expression of intensity of electric field at the axial position due to a short dipole. Next comes the expression of intensity of electric field at equatorial position. Also known as the broadside position. So what exactly is this equatorial position? Suppose these are the two charges of the dipole, minus q and plus q, the distance of separation being 2l. So a point that will be lying on the perpendicular bisector of the line joining the dipole will be known as the equatorial position. Let's say the point P. Okay, and the distance of the point P from the center of the line joining the dipole is r. So from each of these charges, this distance will be L and so will be this distance. So what will be the distance of the point P from each of these two charges? It will simply be root under r square plus L square, and similarly for the other charge as well. So in a similar way, we shall first find out the expression of intensity of electric field due to these individual charges, and then we can find out the resultant. So let E1 be the intensity of electric field at P due to the charge minus q. Therefore E1 will be given as 1 by 4 pi epsilon naught q by the square of the distance, which is root under of r square plus L square whole square. This can be further simplified as 1 by 4 pi epsilon naught q by r square plus L square, and the direction of E1 will be towards the minus q charge. So let's just mark the direction on the diagram. In a similar way, let's find out the expression of E2. So what is E2? Let E2 be the intensity of electric field at P due to the charge plus Q. So E2 will be given as 1 by 4 pi epsilon naught q by root under of r square plus L square whole square. So this you can simplify as 1 by 4 pi epsilon naught q by r square plus L square, and the direction of E2 will be away from the positive charge. So let's just mark it on the diagram. This shall be your direction of E2. Now here there are two triangles. Let's say this point is A, this point is O, and this point is B. So the two triangles have two sides equal. That means they are isosceles triangles. So the two angles will also be same. So if this is theta, this will also be theta, and this angle, being the exterior angle, shall be equal to the sum of the opposite interior angles, that is 2 theta. So here at the point P, there are two vectors E1 and E2, which is separated by an angle of 2 theta. So the resultant intensity of electric field here will be given by triangular law of vector addition, which is equal to E1 square plus E2 square plus 2E1 E2 cos of 2 theta. Here the angle separating the two vectors are 2 theta. Now, if you have noticed carefully, the magnitudes of E1 and E2, they are both equal. So the resultant vector will also be bisecting the angle between the two. This is a property of vector addition. If two equal vectors separated by an angle is added, then the resultant vector will always bisect the angle between the two individual vectors. Now going back to our calculations, if you have noticed that E1, magnitude of E1 and E2, they are same or equal, that is 1 by 4 pi epsilon naught q by r square plus L square. So I'll write E2 as E1 only. So this will be E net is equal to E1 square plus E1 square plus 2 E1 square cos 2 theta. Now from here I can take 2 E1 square common, and this shall be 1 plus cos 2 theta. Now E1 square, once it comes out of the root, it will become E1. So we are left with E1 times root 2 1 plus cos 2 theta. Now what exactly is cos 2 theta? So cos 2 theta is cos squared theta minus sin squared theta, and sin squared theta is 1 minus of cos squared theta. So this gives us 2 cos square theta minus 1. So 2 cos square theta is equal to cos 2 theta plus 1. So instead of cos 2 theta plus 1, we shall substitute 2 cos square theta. So E net is equal to E1 root under 2 into 2 cos square theta, which gives us 2 times cos theta. Now if you look into any of the two triangles, either PAO or POB, you will find that the value of cos theta will be given as, where cos theta is equal to base by hypotenuse, the base being L and the hypotenuse will be root under of r square plus L square. So E net therefore is equal to, what was the value of E1? 1 by 4 pi epsilon naught q by r square plus L square into 2 into cos theta divided by r square plus L square. So in this expression I have basically substituted the values of E1 and cos theta. This can be further simplified as 2ql, which is your dipole moment, as we have seen, by 4 pi epsilon naught, and here there is r square plus L square and also r square plus L square to the power half. So we can just add up the exponents of r square plus L square in this manner. So E net, which is your intensity of electric field, is given by 1 by 4 pi epsilon naught. 2ql is your dipole moment P divided by r square plus L square to the power 3 by 2. This is the scalar expression of intensity of electric field at the broadside or the equatorial position. Now, what will be the direction of our dipole moment? The dipole moment is always directed from negative to the positive charge, that is in this direction, and the E net given in the diagram is actually opposite to our dipole moment. So vectorically, E net shall be written as 1 by 4 pi epsilon naught minus of P vector, because they are in opposite directions. Now, again for short dipole, your R is far greater than L, so R square plus L square can simply be written as R square. So therefore, substituting this condition in the expression of E net is equal to 1 by 4 pi epsilon naught P by R square plus L square, R square plus L square being equal to R square only, to the power 3 by 2. So for a short dipole, the value of intensity of electric field at broadside position is P by R cube. Now, very important question that comes in the board examinations is, for a short dipole, what is the ratio of intensity of electric field at end on to that at the broadside? So E end on by E broadside. And as you may recall that the expression of E end on was 1 by 4 pi epsilon naught by 2 pi r cube, and for broadside position it is 1 by 4 pi epsilon naught into P by r cube. So there will be several cancellations, 1 by 4 pi epsilon naught, P and P, r cube and r cube. So E end on is to E broadside is 2 is to 1. That is, for a short dipole, intensity of electric field at end on position is twice the intensity of electric field at broadside position. This is a very important relation that you may use to solve some numericals. So this brings us to the end of our derivations on intensity of electric field for a dipole. Stay tuned for more videos on important derivations that will be uploaded in the following weeks. Thank you very much.